Okay, for question 1, a regression analysis of student college graduate with their GPAs and their high school GPAs found R squared to be 0.311. Which of these is true? Number 1, high school GPA accounts for 31.1% of the college GPA. That has nothing to do with anything. So, yeah. I said number 2. 31.1% of college GPAs can be correctly predicted with this model. R squared doesn't really mean it's correctly predicted, it just means it's predicted. So number 3, 31.1% of the variability in college GPA is accounted for by the model. Yeah. Okay. Yeah, R squared is a percent of how much the regression model explains variation, not if it's correct or not. And number 2, when using midterm exam scores to predict students' final grade in the class, the student would prefer to have A. I said C, residual equal to 0, because this means the student final grade is exactly what he would predict with the model. I guess I assumed he already got a good grade, therefore it would stay the same, because, you know, good grade is a good grade. However, we don't want those. As a student, you want a better grade, so we want a positive residual, meaning that the observed is bigger than the predicted. So yeah, a positive residual, because this means the student's final grade is higher than what he would predict, higher than we would predict with the model. Let's see here. Yeah. So that leaves A. Alright, for number 3, the correlation between the heights of fathers and the heights of their fully grown sons is R equals 0.52. This value was based on both variables being measured in inches. If the father's height were measured in feet, 1 foot equals 12 inches, okay? And son's height were measured in furlongs. 1 furlong equals 7,920 inches. The correlation between heights of the father and sons would be unchanged. I thought correlation would change because of the unit change, inches being much smaller than furlongs, but we're still comparing the two people being the same height, so relatively, like, there's a dad, there's a son, I'd say relatively the same height. Even if we change the units, it'll be unchanged. So C. What did I say? Yeah, manipulating by a constant to, like, at all just doesn't change unit or anything, or something like that. Yeah, because if we're like, manipulating it. Number 4 on the video said what I picked E was correct. It said that, number C, or letter C, the correlation between distance traveled by a hiker and the time spent hiking is 0.9 meters per second. The correlation between mid-August soil moisture and the per acre yard. So this question is asking for an error. We know that correlation is, we need 2 quantitative variables. A football player plays and is ranked. A position is not quantitative, that is categorical. Of course, gender is categorical, party is categorical too. However, between distance traveled and time, I see that's both quantitative. We found the high correlation between height and age of children. Age of children cannot be, the age of children, it's like categorical. It's like 1, 2, 3. Yeah. And this one, the correlation between mid-August soil moisture, we could calculate. That is also, I picked E because soil moisture, we could like refer to that as quantitative if you're doing like milliliters of water per like square inch or something, and per acre yield of tomatoes. That could also be base quantitative, so I guess E and C could work. Let's see, moving on to 7. A least square regression line for predicting weights of basketball players on the basis of their heights produce the residual plot below. Okay, see, it's a curved pattern. What does the residual plot tell us or tell you about the linear model? Yeah, let's see. A residual plot is not an appropriate means for evaluating a linear model. The curve pattern of the residual plot and the residual plot suggests that there is no association between the weight and height. Curve pattern of the residual. Alright, so we know that the curve pattern for the residual versus height, that means that there is just like the curve pattern shows that it's not like appropriate to use. My mistake though for between B and C, I was like stuck on them, was that I thought B was similar to C, where the curve pattern is a sign of inappropriate residual plot, but B actually meant height and weight are not two quantitative variables, because it says the curve patterns in the residual plot suggest that there is no association between weight and height, but we're looking for, what the heck? Wait. Curve pattern in the residual plot suggests that there is no association between the height. Yeah, and the curve pattern, C is correct because the curve pattern in the residual plot suggests that the linear model is not appropriate. That's just a true statement. I don't know. Wait, well, let me refer to page 160. Actually, wait. In the textbook, if I refer to page 164, if I can find it. Yeah, interpreting correlations. It said, right here. Correlate. Yeah. Correlations should be used only to describe linear relationships. That does not look linear. Okay, let me set this back up with my water bottle. Stay. Alright. 8. Mr. Nerdly asked students in his AP Stats class to report their grade point averages and their SAT math scores. The scatter plot provides information about the student's data. The dark line is the least square regression line for okay. Which of the following statements about the circled point is false? Alright, so we're looking between the correlation of this circle and the line here. The line is a predicted model. This is the actual. Where was I? Yeah, we can see that this is clearly a positive model. So we're looking for the false one. The student residual is negative. It is not negative. It is actually way above the predicted line right here. So yeah. And we can refer to page 191 for this, I think. Let me check. Determine whether a linear model is appropriate for residual plots. Yeah, it says that. Yeah, so if we according to this, the least frequent line clearly does not fit the association very well. For most country average less than 5,000, the actual fertility rates are greater than the predicted results in the positive residuals. It's like an example question about similar to this, where we need to find the positive, like the positive versus negative, like residual, like relationship. And now, part 1, number 2. Well, first of all, I didn't know how to find the y-intercept. I knew how to find b, so like the slope, but turns out if we refer to page 189 using technology to calculate a least square regression, it shows right here that using coefficient of constant and the length of the chord here, these two numbers is directly with the constant being the constant, so like the y-intercept, and then the plus 2.3824 being the the slope. And to interpret it, it's just that I could have just said that x is the length of courtship, and then y is the length of marriage. Let's see. Yeah, interpret the slope in the context of this problem. I could have just said that for each additional year, the courtship, of courtship, we will predict that a marriage will last 2.834 years longer. That's just slope. So like y over x, for every 1 year goes, 2.834 years longer is like the marriage will last longer. Yeah, E right here. Wait. Yeah, E. Yeah, sorry, going for 11 minutes. E. Yeah, okay. A circle point on the residual applies 3, negative 1.04. What is the exact estimate coordinates of the point on the scatter plot that corresponds to the circle point? This is showing work. Okay, so before I did this correction, I didn't know what this question was asking. I was stumped. But now I know that this question is asking for the actual value given the residual, which is this. See, residual versus the residual is negative 1.04. With this knowledge, all I have to do is what I do here, actual minus predicted. Yeah, so this finds the residual. Actual minus is equal to residual. We know we are given that with negative 1.044, where x is equal to 3. With that in mind, we could just plug in, we need to find the predicted value, so then we can find the actual, because we're already given the r. So to find that, we could just plug in, for x is equal to 3 in the equation we got the previous question, which is y hat equals 5.84 plus 2.3824x, plug in 3 for x, and that is equal to 13.0412, which is the predicted value. With this, with all these variables, with the predicted value and the r value, we can now just algebraically solve for the actual, which is what we're looking for, and it equals to 12.0012, and it's looking for the coordinates, so we just plug in 3 in front. These are the coordinates, and we can refer to page 183 for residuals, I think. Let me find it. 23. Residuals. Yeah, residuals. There's like an example problem right here where they did where they use the equation, and then the residual is equal to actual minus predicted, and then plug in what they have just to find what it is. All right, now on to question 2. All right, 30 points. One weekend, a statistician notices that some cars in his neighborhood are very clean, others are quite dirty. He decides to explore this phenomenon and asks for 15 of his neighbors how many times they wash their cars each year and how much they paid in a car last year. His results are in the table below. Okay, so let's see, let's start off with, all right, find the equation of the least square regression. So here I knew how to solve for b, which was the r value times the standard deviation of y over the standard deviation of x. However, what I didn't know what the constant was, because I tried to use it in the y-intercept form. However, I could have just used point slope form because we are given the mean of like these x and y, which is also just the coordinates, so we could just plug it into point slope form over here. So now we see y bar minus 955.30 is equal to negative 60.76 times x minus x bar, which is 6.4, and that would be our equation. Now, to interpret R-squared value in context. Yeah, previously I just used my, wait, where did I get 0.5041? I think I plugged into my calculator wrong, and I don't know what's negative because I squared a negative, but redoing it, we just squared negative 0.71, which would give us 0.504, and R squared is a percent, so we put in a percent value. So 50.4% of the variability in the repair costs can be explained by the linear relationship between car washes and repair costs. Yeah, because the equation, or the problem was asking for, repair costs for last year, number of car washes per year. And now interpret the y-intercept. Previously, I think I was blanking what y-intercept was, but now, fresh mind, y-intercept is where x equals 0. So, in this context, x is the number of car washes per year. So if the number of car washes per year was 0, I would predict he would spend $1,344.18 on repairs. This is from plugging in to the predicted y hat equation. D. Based on the data, can we conclude that the washing your car frequently will reduce repairs? No. However, I said with a low R-squared value, previously I thought that R-squared was about like the variability, and I thought because of the variability being so big, or like being negative, I thought that it just wasn't reliable. However, looking back in the textbook, in page 180, it said that correlation is not always equal to causation, so no. And then it's on page 180, right here. Down there. Correlation is not always equal to causation is about correlation. Yeah, right here. All the correlation is a good way to measure the strength during linear relationship. Yeah, several of them. So right here, correlation does not apply causation. In many cases, two variabilities have a strong correlation, but changes in one variability are highly unlikely to cause changes in another variable. And that is directly related to this question. So yeah.